And so this is, again, a bit of a comprehensive review on the whole course, starting or centering around this molecule HCl. So what is the structure and symmetry of HCl? Okay, let's go ahead and do that Lewis dot thing. This is something that you would have brought in with you from other courses. Do you like your z-axes up and down in general? Okay, so we can go ahead and draw that coordinate system. And so then how would we draw the molecule?
Up and down.
Yeah, up and down. So it would look like this. Okay. That's the one electron from hydrogen and one from the chlorine. How many more does chlorine have? Yeah, so it's got 6 more. It comes in with 7 electrons. So this is our Lewis dot structure for HCl. How do we draw the dipole moment on there? The dipole moment looks like an arrow like this. It has a positive end, and the arrow points towards the negative end of the molecule. So the little plus is, so it should be pointing down. So the dipole should be pointing down. What happens to that dipole moment when the molecule vibrates? So if I stretch that bond, what do you think the dipole moment does? Do you understand what a dipole moment is? And you can ask questions too. But this is, again, a positive end and a negative end. A dipole moment is really like a positive charge. In organic, we would do this. We would do slightly positive, slightly negative. Right? Do you remember that? And so that's what a dipole moment is. We have a slightly positive end of that bond and a slightly negative end of that bond. So if you stretch it, it gets more positive and negative, and if you compress it, it gets less. Okay, and so that dipole moment oscillates with the vibration. It doesn't switch directions, but it does oscillate. When that molecule rotates, though, it does switch directions, and so that would be allowing pure rotation. So we would have vibrational spec with stretching, and then because of the permanent dipole, what is that? What kind of spectroscopy does that permanent dipole allow? Pure rotational. Oops, let me make that a P. So if you make a molecule, if you draw a Lewis dot structure and it's asymmetric and it has a dipole, a permanent dipole, then you know it'll have a pure rotational spectrum. If you draw a molecule like we had in the last exam, this BH3 where it was planar, that one has no permanent dipole. So it has no pure rotational spectrum. Okay. What else can we learn about the structure? Now we could, we're going to kind of do this. We could look at the spectrum of HCl and get the bond length, but let's go ahead and go the other way. I'm going to give you the bond length, and then we'll calculate a whole bunch of other things from it. So this bond length here is 1.27 angstroms. Okay. What else? Okay, so we also have this molecule. What kind of symmetry elements does it have? So let me just list them all. Well, you help me list them. What are the 5 symmetry elements that we talked about? Nobody answer more than one. Okay, so someone throw one out. The 5 symmetry elements. Once somebody gets you started, then you'll remember what we're talking about, okay?
The Cartesian.
The Cartesian coordinates are sort of the frame of space. These are the elements. These are the things you do to the molecules.
Like reflection.
Reflection. Okay, there's the reflection. Okay, sigma V, sigma D, but those are all sigmas. So we have sigma V, D, and H. What are the other four?
Inversion.
Inversion. Good. Someone else give me another one.
Rotation.
Rotation. What kind?
C2.
Yeah, so C, there's a simple rotation, a Cn, raised to the K power, so you can do it twice, and that would be Cn squared. Okay. And then there's two more. One more?
C.
Oh, you've already answered one, so someone else. So there's two more out of the five. One of them we used on every molecule, and the other one we used on very few molecules. So that's probably why you're having trouble. Improper rotation, thank you. So that's an S, N, K. And then the last one, it's on every character table. First column. Identity, yeah, E. So E is identity. Improper rotation, which is also the rotation reflection. So it's a sigma H operating after a Cn. So we do a rotation around, actually it's Cn over 2. Let's see. No, we'll leave it like that. You know, you rotate it like a S6 would be rotated 1/6 of a turn and then reflect it through the horizontal plane. If you need to review those, where would you go? What website? Do you remember the name of it? SimOtter, yes. I can't remember .org or .com, so just Google it. The links are in Blackboard, of course. Okay, so with those five, these are symmetry elements. When a molecule possesses more of those, it's more symmetric. So you would kind of count up how many of those things the molecule possesses, and that's when we say this molecule is more symmetric than the other. So like a C1 only has one symmetry element, and that's the identity. A Ci would have identity and inversion. A C2, I think it just has the identity and a C2 rotation. CS only has the reflection plane. So those are very low symmetric, not very symmetric molecules. This molecule has an infinite number of symmetry elements. And what are they? It has the identity. Okay. What other kind of symmetry elements does it have? We've got four choices here.
Rotation.
Yeah, proper rotation. So it's got that. In fact, it's a C infinity. So this axis right here, if we rotate it around that axis, C infinity. Okay. So that means that N is the number of, that's how you divide 360 degrees, right? So you can divide it by infinity. You just turn it an infinitesimal amount and it looks the same. And so again, we make that judgment like this BH3 down here, we have to turn it a whole third of a turn before it looks the same. Whereas HCl, we turn it just a tiny infinitesimal amount and it looks the same. So it's a C infinity axis. There are an infinite number of one of the other symmetry elements. You know which one that is. So does it have an inversion? It can't have an inversion because the H is on top, the Cl is on bottom. You can't invert those into each other. They're different elements, and so that's not an inversion, so it doesn't have that. The improper rotation, you reflect down, so there's nothing below the molecule or below the center of mass that looks like what's above it, so you can't have an improper rotation. So it should have a reflection plane. So in the plane of the paper, and I think a lot of people have trouble seeing reflection planes in planar molecules because the molecule, if it's a planar molecule, it fits in the plane. The top half can reflect into the bottom half, and so that's legit. So it has an infinite number of these reflection planes, and so it would have an infinite number of sigma v's. Okay, so if we go through the character tables or the flow chart and we look to see what the point group for this molecule would be, we end up with this point group designation of C infinity V. And I always sort of put a square around those to emphasize that that's a point group, not a symmetry element. See, we have a symmetry element here of a C infinity axis. We have an infinite number of sigma V's, but I don't put squares around any of those. I just put the square around the point group, so we know that's our point group. We can look that up in the character table. Okay, so we know a ton about HCl and its structure. Okay, since we've got the Lewis dot structure, how many peaks would we expect? This is jumping way to the end of the course. If local bond theory were accurate. So number, I'm just writing down here, number of valence electron peaks from LB theory. LB standing for local bond theory. So we just look at the types of electrons. So we have a bonding electron pair between the H and the Cl, so that's one type of electron. And then we have the non-bonding electrons. Even though there's 6 of them, that's still a second type of electron, so we just need 2 peaks. Now later on we'll get to the MO diagram. We'll do an MO diagram for this and we'll see what kind of peaks we would see. Okay. All right, so now let's look to see what HCl can do. This is all about its structure, its point group, what we'd expect from the electron spectroscopy. Well, since we're doing, well, let's go ahead and look at what kind of things it can do. Okay, it can translate. It can rotate, it can vibrate. The electrons can be excited by light, and the nuclei can be excited by NMR. That you learn about that in organic. I think is that organic 2. And so what is the energy for translation? Okay, it's going to be this particle in a 1D box. So that is our classic energy for translation. It has the quantum number here, N. It has the size of the system, the length of the box. It has the mass. And so we could add up the mass and figure out what kind of energies we'd have. It has Planck's constant. So we know all of these terms. We know how this energy equation is, so this will definitely be on the test. On any of the equations that we have, you need to know or be able to determine how the energy changes with mass, how the energy changes with size, how the energy changes with quantum number. Okay. And so let's just do that here for this one as N goes up, energy goes up. Okay. As M goes up, energy goes down. And as L goes up, energy goes down. You see that? Can you look at that and tell? Now, now you can put some math to that. If we double the box, what will happen to the energy? So let's do one of those quick questions here. I love these kinds of questions because if I say you've got a particle in a box and you double the size of the box, what happens to the energy? You're looking at that and you're saying, well, I don't know what quantum state I'm in. I don't know what the mass is. So how can I do this problem? I've got a question that's asking me about a variable in this equation, but I don't have all the other variables. So you can't just plug everything in and answer it. And so if I've got E1 and that's h squared, I'm going to put a 1 on the n quantum number, n1 squared over 8 m1 l1 squared. And I want to know its ratio to E2. I'm just going to write all that again, h squared n2 squared over 8 m2 l2 squared. And I say, what happens when I double the length of the box? Okay, I have to assume that the quantum number has stayed the same, so it cancels. Planck's constant is Planck's constant. Okay, it's not changing. 8 hasn't changed. The mass hasn't changed. The only thing that's changed is L. And so I can cancel all of that stuff and come up with a new equation now. So I have E1 over E2 is equal to L2 squared over L1 squared. Can everybody see that? My L2, 1 over L2. Okay, and so then L2, like I say, I doubled the box. So I have a 2 times L1 is L2. That's what I mean by doubling the box. And you can see that the L1 squareds are going to cancel. Okay, and I'm left with 2 squared. So this E1 is going to be 4 times greater than E2. So if I double the box, it shrinks by a fourth. I can swap that around, solve for E2 is equal to E1 over 4. So if I increase the box length, the energy should drop, and E2 is 1/4 of the energy of E1. So that's the best way to do those kinds of problems. I don't have to assume anything for the quantum number. I don't have to assume anything for the mass. I'm just using the change in box. Now you can do this with anything that's proportional. So I could have said that E is proportional to 1 over L squared. And anytime you have a proportionality, you can jump right to an equal sign if you do this 1s and 2s. E1, E2 is equal to 1 over L1 squared, 1 over L2 squared. And we can get rid of that proportionality. So anytime you hear something's proportional to something else, you can turn that into an equation if you have a case 1, case 2. And that's a skill I want everybody in this course to know. We've done several problems like this in the homework or on the exams. That is a take-home skill. I want you to have that skill going forward. You can do the same thing with vibrational frequency. Vibrational frequency, you could write this out. Vibrational frequency is proportional to the square root of 1 over mu. Okay. So you could turn that into an equal sign by putting 1s and 2s on everything. So we can do that here. If you wanted to, so nu 1 over nu 2 is equal to the square root of mu 2 over mu 1. See, I'm looking at that. I've got mu, and on the other side is in the denominator mu. So 1, if I'm looking across the equal sign, mu 1 is on the denominator. if nu2 is in the denominator, look over on the equal sign, and mu2 is in the numerator. Okay. And so there's your equality. If I change the mass, this is what's going to happen to the vibrational frequency. Let's go ahead and put numbers on this one. So our vibrational frequency, let's do the vibrational frequency for H35Cl and the vibrational frequency for H37Cl. Okay. So I have H37 reduced mass on top and H35 reduced mass on bottom. Not going to be much change. Now we looked up when we did some early, I think it was on a homework, the vibrational frequency for H35Cl was like 2830, say. Let me see if I've got it in here. $28.50. All right, so we know this number here. We can calculate all these others. So just quickly, let's calculate the reduced mass of HCl37. So we have our reduced mass equation up here. So mu, let's do 37. Is that a good shorthand for us? So we have 1 times 37 over 1 plus 37. This again is an estimate since we're just doing quick calculations. So someone calculate 37 over 38 for me. Yeah, pull out your phone or your calculator. I'm probably going to need 3. 974. Okay. Okay, now let's do mu 35. So 1 plus 35, 1 times 35, sorry. Over 1 plus 35. And in terms of our exams, these are going to be the kinds of reduced masses that I'm using, so you can assume those things. Because again, for exam, you're just doing quick calculations. For your labs, you'd want to use 37 point whatever, all 13 digits. Okay, so this one? Yeah, 0.972. Okay. So let's put these in their correct places. We have the square root of 0.974 over 0.972. So take that ratio and take the square root for me. Who's got it? Okay, so 1.001. It's a unitless quantity because all of the mass units have canceled. And so this is saying that the HCl37 frequency, let's see, 35 should be, 35 should be about 1 part per thousand higher than HCl37. So let's rearrange this. HCl37, the frequency of HCl37 is 2850 wave numbers divided by 1.001. So is it what, 2849 or something like that? 2847. Definitely a measurable difference. And so when we did our, when we looked at HCl and the homework and so on, you saw those doublets in the HCl 35 and 37, and that was the mass effect. And it was dependent upon the inverse of the square root of the reduced mass. And so that's using this equation right here. Notice we could do that whole thing without knowing the force constant, because the force constant between HCl 35 and 37 is the same. Now, why would that be? Let's think about the science behind the force constant. What is the force constant in terms of physics? It's just that spring that's holding the two atoms together, right? And it's how tight that spring is. Now, in a molecule, what makes that spring tight or loose? What's holding those atoms together? The what? The bond. But what makes the bond? The electrons. It's that electron cloud, right? And so that electron cloud is the same in HCl 35 and 37. Why? What's the only difference between HCl 35 and 37? A couple of neutrons. And they don't change the electrical field at all. They're not charged. So we still have the same number of protons in chlorine and hydrogen. We still have the same number of electrons. So that force constant, it's good to assume that that force constant's the same. Okay, so we can cancel that out and just ignore it. And the only thing that changes is the mass. So this isotopic substitution, when we put in a 37 or a 35, we can see a slight shift in the vibrational frequency. Okay. Here are the energy equations. We did the energy for the 1D particle in a box. That's the translational energies. If you're going on to thermodynamics, we're going to start right there and look at how heat affects gases and so on. And so we'll look at those heat effects. We see up here, these are sort of the average kinetic energy for a macroscopic object. For gas molecules, Boltzmann proved that it was related to the gas constant. This is actually Boltzmann's constant times Avogadro's number, the R gas constant. It's related to temperature. Here's the energy equation for rotation, and it's related to this rotational constant, B. And then we did that whole thing, I called it in the notes, note card bait. This has got all of those constants of Planck's constant and the conversion from meters to angstroms squared and all of those things. This is our rotational constant as it depends upon the reduced mass and the bond length. Notice how it depends upon the bond length squared, which is kind of interesting because, you know, the translational motion also depended upon length squared in the denominator. Rotational motion depends upon length squared in the denominator. Mass is in the denominator. So even as mass increases, the rotational constant goes down. And as the rotational constant goes down, energy goes down. So there we have like 3 steps in it. So we have as mu goes up, B goes down, and energy goes down. You see how they're connected? Through B, we get to the energies. Same kind of thing. As mass goes up, energy goes down. As R goes up, what happens to B? It goes down by R squared even, and then energy goes down. Okay. Now where's the quantum number? Quantum number is not in B. It's over here. These are the quantum numbers. So J is our quantum number. As J goes up, energy goes up. So once again, as you increase the quantum excitation, the energy goes up. That's natural. You would imagine that, right? Let's look at vibrational frequencies. So notice the energy is related to that vibrational frequency, and the vibrational frequency is related to the mass and the force constant and so on. So as mass goes up, vibrational frequency goes down, and therefore energy goes down. So once again, the mass energy effect is the same. It may have a different power, like a 1/2 power or something like that, but as mass goes up, the vibrational frequency goes down and energy goes down. We have a new thing here, this force constant. So as K goes up, the vibrational frequency goes up and energy goes up. And then this is V, this is our quantum number. And naturally, as it goes up, quantum number goes up, energy goes up. Okay, H and C, those are constants, so we don't change those. But you have the Planck's constant and the speed of light. I will assume that you know what this little tilde means, okay? So you need to, let's reinforce that right now. What is this little tilde trying to tell you? When I put a tilde on these things, I'm telling you something about them. Do you know what I'm trying to tell you? That means the units are wave numbers. Okay. I think that's all we can put on this slide. Okay. Any questions about any of these equations? These equations should definitely be on your note card. Now, maybe not this one. We're not really going to use this one. I just put that up there for translational motion. That's in semester 2. Okay. Yes.
Like, are we making a new note card for this, or are we just using all of our note cards for this?
Oh yeah, you can make a new note card for this. Yeah,
Do either?
you can use all of them and then make a new one. So you get one new note card for every exam. So this is an exam, so you can make one more. If there's like something you really like clued in on, you can put that on your new one instead of trying to squeeze it on an old one. Okay. And most of the time, it's just the educational benefit of making the note card. That's what I'm after. Because when you're trying to decide what to put on that small space, you have to really think about what's important, and what you need help with. So it's a self-reflecting thing, and it's just a reinforcing thing to go ahead and write it out. And it's a test of how small you can write. That's always helpful. Yeah. Okay, so let's draw energy level diagrams for HCl for all of these. Okay, so energy, when we talk about an energy level diagram, it's exactly that. The energy is on the y-axis, and we just have energy levels there. Sometimes the x-axis means something, like in vibrational motion, we have the internuclear distance, it's stretching. But in the rotation and translational motion, the x-axis or x direction doesn't really mean anything. We just draw a line, and that's the energy level, and we label them with quantum numbers. Okay, so for translational motion, E equals h squared n squared over 8 ml squared. So this will be for a particular mass or for a particular length. Planck's constant and 8, none of those change. So all we're really dealing with is n. So it's important in your energy level diagrams to get the spacing at least moderately correct, right? So this is n equals 1. For translation, we don't have an n equals 0. Equals 2. Now I need to make a decision. Do I put the next level here where they're equally spaced or not? What do I do? They're not equally spaced, right? So n equals 1 would be this constant times 1, but then n equals 2 would be this constant times 4. Okay, so this is 1, 2, 3, 4. What's the next one going to be? It's going to be times 9, right? So it's going to be like almost double that difference. And the next one's going to be 16. If this is 9, it's almost, almost double that. And that we're kind of out of room now. But do you see how I want to see, like if you were to draw this, I want to see that the spacing of the energy levels is not the same. It's n squared. Okay. Now for rotation, the J quantum number, okay, let's go back. It's look at the previous slide. It's B times J plus 1. There's an HC in there. I guess I could put those. HC times B in wave numbers just gives you joules for the energy. So B times J plus 1. So this is the way it's traditionally written for rotational systems and even like the angular momentum of the orbitals. But it could have also been written J squared plus J. Okay, but this is the traditional way to write it, J times J plus 1. But it is J squared. So once again, we have energy levels that are not equally spaced. These also have degeneracy. So G of J is equal to 2J plus 1. So the degeneracy is shown in the energy level diagram too. And we have a J equals 0. So down here, for J equals 0, what's the degeneracy? If J is equal to 0, 2 times 0 plus 1 is just 1. So we just have one energy level there. So now for the next one, J equals 1. Okay, so 2 times 1 is 2 plus 1 is 3. So for J equals 1, we have 3 energy levels. And again, they go up as J squared. So I've set the first gap. Now where's the next one go? It's going to be kind of like this N3. It's going to be up here somewhere. Okay, so it'll be up here. What's the degeneracy for J equals 2? So 2 times 2 is 4, plus 1 is 5. So we have 5 energy levels here. All right. Then we get up to J equals 3. So 2 times 3 is 6, plus 1 is 7. And so we end up here. 1, 2, 3, 4, 5, 6, 7. And I guess we could squeeze another one up in here. So J equals 4. 2 times 4 is 8, plus 1 is 9. Is that correct? Let's see. 4, yeah, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And they're not equally spaced, so it goes as J squared. So those are the energy level diagrams for translation and for rotation. Now for vibration, we can be a little bit more creative. We can actually have an x-axis. And so for vibration, let's draw an x-axis. And we've only really dealt with diatomics in this course. I used to walk before you crawl, right? And so this would be the distance between the nuclei. We'll think of it as a stretch. And this is about HCl, so that makes sense. It's a diatomic. All right, and then do you know what kind of potential energy we'll have for vibrational motion? What does it look like? For translation, we had 0 potential energy, right, inside the box. We said there's no potential energy inside the box. For rotational energy, it was a free rotor, so there was no potential energy for rotating this molecule. But for vibration, we have that force constant. Okay, and what's the model that we use? What's the name from physics? It's the pendulum. What is that name of that system? Harmonic oscillator, right? So what is the potential energy for a harmonic oscillator? It's a parabola, right? Wow, that's the best one I've ever done on this pad here. Okay. All right, so that's our potential energy surface. And then in here we have our vibrational frequency. Okay, this we can decide on what we call zero. Anyway, let's call this RE. Let me scoop this up a little bit. That's our equilibrium bond length. And that's what we were solving for in all of those labs was RE, that bond length at the minimum of that potential surface. And we're going to draw our energy level here. And that's going to be V equals what? 0 or 1? You have to make a decision on all of these. For translational motion, it starts with 1. For rotation, it starts with 0. What does vibration start with? 0. Yeah. So remember your iodine lab, right? You had 0, 1, and 2 for the lower states, and up there you had a bunch of different ones, but V equals 0 is the lowest one. Okay. Our energy equation up here is equal to that vibrational frequency. I guess you could do the HC again, times V plus 1/2. So what is this energy? If this right here is at 0, what is this energy right here? It's 1/2 of the vibrational frequency, right? So I've got V is equal to 0 plus 1/2. So 1/2 times the vibrational frequency. So 1/2 of nu. And then I have V equals 1. So I'm going to draw that level here. And that's the vibrational frequency times 1.5, right? V plus 1/2, 1 plus 1/2. What if I go to V equals 2? I need to make a decision on the spacing. Look at the quantum number here. What's the power of that quantum number? It's linear with the quantum number, right? And so it's going to be equally spaced. So this one is equally spaced. So we can call these, we call it an equal ladder of states. So this next one is V, or the vibrational frequency, nu times 2.5. And this one is nu times 3.5. You see the difference between all of those is just 1 unit of the vibrational frequency. So if you know the vibrational frequency, you know the spacing in the energy level diagram. And so that gets us to the energy level diagrams for all of our different types of motion, translation, rotation, vibration. And on the next time, we'll get into the spectroscopy of it all. So we're out of time today. But this, again, you know so much about energy levels and quantum numbers and how to manipulate the equations. And we'll just continue on with that on Wednesday. And hopefully we'll finish about halfway through Wednesday and you can ask general questions. Okay.